Hi everybody, today we're going to continue with our complex circuits, and the first thing I want to do is point out a typo I had in my last video. I didn't realize it at the time, but I had not typed this 0 when I went to do my recalculation for the first circuit. So it should come out to a total resistance of 54 ohms. Because when I had this as 0.4, it gave me the incorrect number. So the correct value for the total resistance is 54. Now that we have that out of the way, what we're going to be doing today is determining the current and voltage and power for the three resistors that are connected in this circuit. So our first step for doing that would be to find the total resistance, which is what we did yesterday. So now that we have that done, now we're ready to work on the circuit. So we said that this was basically a series circuit with a parallel branch inside it. So if I treat this as if there is this made up imaginary resistor inside it that is 24 ohms, that would just be a series circuit with a 30 and a 24. And we already know how to deal with that. The voltage we know on the whole circuit, so I'm going to call that the total voltage, is equal to whatever the battery is. And I can then find the total current by saying V divided by R, or 25 divided by 54, which was my total resistance. And that gives me 0.463 amperes, or you can just say 0.46. Now that number does make sense because series circuits tend to carry lower currents. Okay? Now that I know my total, now I want to get my my voltage and my current for each individual resistor. So if I just look at my circuit with my imaginary resistor, I'm going to forget that the imaginary resistor really is these two. I'm going to treat it as if that imaginary one is right there. I'm going to get the voltage, current on the 30 and on the 24. Now the current on the 30, because this is in series, is the same as the total. That's going to be the same as the current through the 24, but let's find the voltage first. The voltage on the 30 is going to be I times R. So that's 0.46 that we just found times my resistance of 30. And that equals 13.8. I'll then do the same thing for my imaginary 24. I on the 24 equals 0.46 amperes. Now that should make sense because it's in series with the 30. And in series, they all have the same current, and it's equal to the total current. So my voltage, I'm going to find the same way, which is going to be 0.46 times 24, the resistance, and that gives me 11 volts. Okay. Now I'm going to chew my check. We said that the voltage should add up, when I've done all of my resistors, the voltage should add up to be what the battery is. So 13.8 is about 14. 14 plus 11 is about 25. So we know we've done that correctly. Okay, I'm going to do my power all at the end, so we'll get back to that. Now I'm going to have to forget that this is an imaginary resistor. And I'm going to have to actually deal with the 40 and the 60 that are in parallel. Well, I remember in parallel, what is constant is voltage. So that means that the voltage on the 40 is equal to the voltage on the 60, and that happens to be whatever the voltage was that was going through my imaginary 24. So both of them have a voltage of 11 volts. So now I can get their individual currents. So for the 40, I on the 40, that's going to be its voltage divided by its resistance, or 11 divided by 40, and that gives me approximately 0.28 amperes. I'll now do the same thing with the 60. My voltage divided by its resistance, and I get 0.18. Now, if I add those two together, 0.28 plus 0.18, that adds up to 0.46, which we said was the total current going through that part of the circuit. So we know we did that right. That's the great thing about circuits, is they have these built-in checks for you. Well, now that I have the voltage and the current on everything, now I can find the power. And I'm only going to find the power for resistors that actually do exist, so not my imaginary 24. So the power on the 30, that's going to be equal to I times V. Now there are other ways to find power, but this is the easiest way. That's going to be equal to my current of 0.46 times my voltage, which we found to be 13.8. That gives me 6.3 watts. I'll then do the same thing for the 40, which is going to be the current that it has, which was 0.28, 0.275, I'm going to leave it as 0.28, times its voltage, which we said was 11. That gives me 0.31 watts. And then I'll do the same thing for the 60. That's 0.18 times 11, which gives me about 2. So if we were looking at this circuit, if they were light bulbs, the 30 would burn the brightest. It would be a lot brighter than the other two. But again, it's pulling the most power from the battery. It's going to burn out relatively quickly. And when it burns out, the others will go out too, because it will basically put a break in my circuit. Okay, so that's the first problem. Okay, now we also did the second one yesterday. So I'm going to put the second one over here. Now, we remember we got for our total resistance, we got, I did not write it down. Just checked my stuff from yesterday. We got 18 for our total resistance. Okay, so that is for this circuit right here. So my resistance overall was 18, and that's 18 ohms. Okay, now that I know that total resistance, I can get my total current. Now, I don't actually need to do this step, but I want to know what that total current is so that I can compare my answers to be sure that I've added everything up right. So that's going to be my voltage, which again is my battery, divided by my resistance. So 50 divided by 18, and that gives me 2.8 amperes, which is a fairly high current. It seems like it's a low number, but it actually is pretty high, especially if you compare it to the current that we saw in our first problem that we did. Okay, now that I know my total, I can then start to analyze the individual components. Now, as we said, this is basically a parallel with a series inside it. In parallel, what is constant is my voltage. So that means the voltage on the 30, I'm going to do the 30 first because it's by itself. The voltage on the 30 is going to be the voltage of the battery. Now that I know that, I can get its current. So the current on the 30 is equal to its voltage divided by its resistance. So 50 divided by 30, that gives me 1.67. Simplify that a little bit. My other element, my 20 and my 25 combined, that gave us 45, if you remember. So the voltage on that imaginary 45 is also 50. But it is going to carry a different current because in parallel, currents vary. So my current there, I'm going to find the same way. The voltage, which was 50, divided by 45, and that gives me 1.11. Nope, that should be amperes. And that should be amperes. Okay. Now, if I add these up, 1.67 plus 1.11, I get approximately 2.78, which is exactly what it should be. I can now separate these two into their real resistors. So I'm going to find the voltage. I know the current. I know that the current on the 20 is 1.11, what we just found, and I can now find its voltage. I'm going to find its voltage by saying V equals IR, okay, or my current, 1.11, times my resistance of 20, and that gives me 22 volts. I'll then do the same thing for the 25. That's going to be, also have the same current because they're connected in series. So my voltage is going to be 1.11 times 25, which is 27.5 volts. Now, if I add those two together, 22.2 plus 27 point, we'll make this 27.8, just to round it, that will both add up to 50, which was the voltage of that part. Now all that's left for me to do is to find the power. Power, we said, we just do P equals IV. Okay, so the power in the 30 would be, I was 1.67 times 50, which gives me 83 watts. And then I would do the same thing for the other two.